Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual crucible of the mid-18th century, few questions burned with greater intensity than the true figure of the Earth. This was a query that transcended mere cartography, touching upon the very architecture of the cosmos and the validity of competing physical worldviews. It was a contest pitting the gravitational theory of Isaac Newton, which predicted an oblate spheroid flattened at the poles, against the vortex mechanics of René Descartes, championed by the formidable Cassini dynasty in Paris, whose geodetic survey suggested a prolate spheroid, elongated like a lemon. Into this charged arena of scientific debate stepped Alexis Claude Clairaut, a mathematical prodigy of astonishing power. His 1746 treatise, Théorie de la figure de la Terre tirée des principes de l'hydrostatique, stands as a monumental work of synthesis and clarification. It represents a watershed moment in the history of science, a masterful unification of Newtonian mechanics, fluid dynamics, and advanced mathematical analysis that permanently transformed geodesy into a physical science and laid the foundational stones for the edifice of modern potential theory. Clairaut's work resolved the central controversy of its day, and in doing so, forged a new and powerful methodology for interrogating a physical. The intellectual landscape Clairaut entered was one of profound tension between theoretical prediction and empirical measurement. In his Principia Mathematica of 1687, Newton had conducted a brilliant thought experiment involving two communicating canals of water, one running from the pole to the Earth's centre, the other from the equator to the centre. By balancing the pressures exerted by these columns, accounting for the centrifugal effect of rotation on the equatorial canal, he deduced that the Earth must bulge at the equator and be flattened at the poles. His calculation yielded a flattening of approximately 1 part in 230. This theoretical conclusion, however, faced a formidable empirical challenge from French astronomers. From the late 17th century through the early 18th, Jean-Dominique Cassini and his son Jacques Cassini undertook painstaking measurements of arcs of the meridian at different latitudes across France. The results, published in 1720, consistently indicated that a degree of latitude was longer in the south of France than in the north. This implied a prolate, or egg-shaped, Earth, a finding that provided powerful ammunition for the Cartesian camp and was seen as a direct refutation of Newtonian attraction. The Paris Academy of Sciences, caught between English theory and French measurement, found itself at an impasse. The resolution demanded more decisive data. This impetus led to the famous geodetic expeditions dispatched in the 1730s, one to Peru, near the equator, led by Pierre Bouguer and Charles-Marie de la Condamine, and another to Lapland, inside the Arctic Circle, led by Pierre-Louis Maupertuis. Clairaut, already a celebrated member of the Academy at a young age, was a key scientific figure on the Lapland expedition. The brutal, frozen landscape of the north provided the theatre for measurements that would ultimately vindicate Newton. Yet, the raw data itself was insufficient. It required a comprehensive theoretical framework to interpret the measurements, to connect the observed length of a degree of arc and the period of a pendulum to the underlying shape and mass distribution of the planet. This was the profound challenge that Clairaut addressed and conquered in his Théorie de la figure de la Terre. The genius of Clairaut's 1746 work lies in its radical and elegant conceptualization of the problem. He began with a powerful physical assumption: the Earth is a rotating mass of fluid in hydrostatic equilibrium. This idealization, treating the solid Earth as if it were a liquid that has settled into its final form under the combined influences of self-gravitation and rotation, was the crucial first step. It allowed him to move beyond simple geometry and apply the rigorous principles of fluid mechanics. This approach led directly to his most profound insight: the surface of such a body must be an equipotential surface. He demonstrated that for a fluid to be in equilibrium, the direction of effective gravity, which is the vector sum of the gravitational force and the outward centrifugal force, must be everywhere perpendicular to the surface. Any component of force tangential to the surface would induce a flow, violating the condition of equilibrium. A surface to which the net force vector is always normal is, by definition, a surface of constant potential. This single concept reframed the entire problem. The question was a physical one about the shape of a level surface, a shape dictated by forces, a discovery of far greater consequence than a purely geometric description. This elevated the discourse from measuring shapes to understanding of physical principles that generate them. To manage the immense mathematical complexity of this model, Clairaut developed the analytical tools that would become the bedrock of potential theory. He sought to calculate the gravitational potential of an arbitrary, nearly spherical, rotating body. His method involved expressing the potential at an external point as an infinite series, a technique that was a direct precursor to the formal development of spherical harmonics. By Adrien Marie Legendre and Pierre-Simon Laplace decades later, Clairaut essentially pioneered the use of these functions to solve physical problems, demonstrating how to approximate the potential generated by a body of non-uniform density. He showed that the potential could be broken down into terms corresponding to different degrees of deviation from a perfect sphere, a method of extraordinary power and flexibility. This mathematical apparatus allowed him to move from the abstract principle of an equipotential surface to a concrete, calculable relationship between the planet's shape and its gravitational field. A touch of historical irony lies in the fact that Clairaut forged these powerful tools in the service of a specific problem, perhaps unaware that he was laying the groundwork for a mathematical language that would later describe everything from electromagnetism to quantum mechanics. The culmination of this theoretical edifice is the celebrated formula known as Clairaut's theorem. The theorem provides a direct and elegant relationship between the Earth's flattening and the variation of gravity on its surface. In its mature form, it states that the sum of the flattening, represented as the ratio of the difference between the equatorial and polar radii to the equatorial radius, and the ratio of the difference between polar and equatorial gravity to equatorial gravity, is approximately equal to 5/2 of the ratio of the centrifugal force to the force of gravity at the equator. The true elegance of this relationship is its remarkable independence from the specific details of the Earth's internal density distribution, with the sole condition that the density is arranged in concentric, hydrostatic layers. This was a result of stunning practical importance. It implied that one could determine the Earth's geometric flattening by performing purely physical measurements on its surface, namely, by timing the swing of a pendulum at different latitudes to measure the local strength of gravity. The quest for the Earth's shape was thereby liberated from the monumentally difficult task of measuring meridional arcs. Clairaut had provided a theoretical key that could unlock the planet's secrets from simple, local experiments. The immediate impact of the theory was decisive and profound. Upon returning from Lapland, Maupertuis had announced that their measurements confirmed an oblate Earth, earning him the affectionate, if slightly mocking, title of the Earth Flattener. Clairaut's book, published a few years later, provided the unassailable theoretical foundation for this empirical result. It explained precisely why the pendulum swung faster in Paris than at the equator, and why a degree of longitude was longer in Lapland than in France. It united the pendulum measurements and the arc measurements within a single, coherent, and mathematically rigorous framework, ending the long and often bitter controversy between the Newtonians and the Cartesians in a resounding victory for Newton's theory of universal gravitation. The work transformed geodesy overnight. The field was elevated from a process of surveying to a sophisticated branch of mathematical physics. Geodesists were now armed with a theory that told them what their measurements meant in a deeper physical context and how different types of observations could be cross-referenced and validated. The legacy of Clairaut's work extends far beyond the 18th century resolution of the Earth's shape. His development of potential theory was a direct and acknowledged influence on the next generation of French mathematical physicists, most notably Laplace. In his monumental Traité de mécanique céleste, Laplace took Clairaut's concepts, generalized them, and placed them at the very heart of celestial mechanics. The famous Laplace equation, stating that the Laplacian of a potential function is zero in free space, is the direct intellectual descendant of Clairaut's analysis of the gravitational potential of a nearly spherical body. The mathematical language Clairaut began to articulate became the lingua franca of 19th century physics. Furthermore, Clairaut's fundamental insight that surface gravity variations contain information about the interior of the planet is the foundational principle of modern geophysics. While he assumed a simple hydrostatic model, later geodesists like Carl Friedrich Gauss and Friedrich Bessel would refine the concept of the Earth's figure, leading to the modern idea of the geoid, which is nothing a physical manifestation of the equipotential surface that Clairaut first conceptualized. Every time a modern geophysicist uses satellite gravimetry to map density anomalies in the Earth's mantle or prospect for mineral deposits, they are standing on the intellectual shoulders of Alexis Clairaut. His work established the paradigm at external field measurements can be used to infer the internal structure of a physical body. The reception of the theory was one of widespread acclaim within the scientific community, which recognized it as a work of supreme elegance and definitive power. It was Clairaut's magnum opus, cementing his reputation as one of Europe's leading mathematicians. Yet, the intellectual climate of the Parisian Academy was one of intense, almost gladiatorial, rivalry. Clairaut's work proceeded in parallel with that of another brilliant mathematician, Jean-Laurent de L'Alembert, who was also attacking the problem of the Earth's figure and precession. Their relationship was complex, a mixture of mutual respect and sharp competition, with disputes over priority and method occasionally flaring up. This creative tension, while personally taxing for the individuals involved, likely spurred both to greater heights of rigor and creativity. D'Alembert's work on the precession of the equinoxes, for instance, complemented Clairaut's research on the Earth's static figure, together providing a near-complete dynamical theory of the rotating Earth. Despite these rivalries, the clarity and comprehensive nature of Clairaut's 1746 treatise gave it a singular authority, making it the standard reference on the subject for decades to come. In conclusion, Alexis Claude Clairaut's theory de la figure de la Terre is far more than a solution to an old problem. It is a landmark of scientific methodology and a testament to the unifying power of mathematical physics. By treating the Earth as a physical system governed by the laws of hydrostatics and Newtonian attraction, Clairaut transcended the limitations of both pure theory and pure empiricism. He forged a new synthesis, one in which mathematical analysis provided the indispensable bridge between abstract principles and concrete, measurable phenomena. The work's central achievements, the concept of the equipotential surface and the formulation of his celebrated theorem, armed scientists with a powerful new way of understanding the planet. This achievement resolved a foundational debate of the Enlightenment, but its true significance lies in the paradigm it established. Clairaut demonstrated how to construct a predictive, quantitative model of a complex celestial body, a method that would be refined and extended by luminaries like Laplace and Gauss to build the grand structure of classical mechanics. His 1746 treatise is a work of enduring brilliance, a foundational text that shaped the course of geodesy, geophysics, and theoretical physics, forever changing how we measure and comprehend our world.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.